Welcome to this explainer. For the next 10 minutes, we're plunging straight into the terrifying, raw mechanics of extreme ocean storms and how human beings have somehow learned to survive them. We're going to move fast and throw a ton of fascinating, rapid-fire information your way, so keep your eyes glued. You are not going to want to look away from this. We're talking about the sheer, untamable power of the sea, from the atmospheric mechanics of a hurricane to the jaw-dropping reality of towering rogue waves out in the deep blue. Picture this. You're standing on a ship's bridge, staring out into the pitch-black open water of a midnight squall. You have absolutely nowhere to run, as an impossibly massive, jagged cliff of water just emerges from the darkness, towering 84 feet right above your head. What happens to the vessel in that fraction of a second? And more importantly, what happens to the people inside? You see, when the ocean reaches this level of violence, the storm isn't really just weather anymore. It behaves like a living engine of chaos. It consumes, it grows, and it moves with this almost terrifying sense of purpose. To truly wrap our heads around how we even attempt to survive these extremes, we really need to understand how this colossal engine is born in the first place. Section 1. Birth of a monster. Okay, so how does a hurricane actually start? Well, it begins deep in the ocean with one incredibly simple ingredient: heat. Warm ocean water fuels rising moist air. As that moisture-rich air rapidly rises into the atmosphere, it releases its stored heat, which creates this powerful low-pressure vacuum underneath. That vacuum then pulls in surrounding winds, creating a massive snowball effect. Before you know it, you've got isolated thunderstorms clumping together, aggressively feeding off the ocean's surface energy and building into a massive, rotating monster that can literally tear apart entire coastlines. And right in the middle of all that swirling madness, the eye. It's a deceptive, weirdly peaceful center that can be up to 50 miles wide. Inside the eye, the winds just die down, and the rain totally stops. You might even see sunlight piercing through the clouds. But do not be fooled. This sudden, eerie silence is a trap. Historically, it's tricked so many sailors into thinking the danger has finally passed, but it's really just a brief pause before the back half of the storm hits, bringing 150-mile-per-hour winds slamming into the vessel from the exact opposite direction. Section 2. Measuring the wind. For centuries, we had absolutely no standardized way to measure this escalating chaos. Before 1805, assessing the wind was basically just guesswork. One sailor's light gust was another's severe gale, which, as you can imagine, made naval logs incredibly confusing to read. That is, until a British Royal Navy hydrographer named Francis Beaufort came along. While serving on the HMS Woolwich, he devised a brilliant, unified system that quantified the wind's power based purely on its physical effects on a ship's sails. By the late 1830s, the Royal Navy officially standardized this scale, forever changing maritime history. The Beaufort scale was an absolute game changer. It finally gave sailors a vital, objective metric to communicate danger. Just look at the contrast here. A force 0 represents a completely calm, mirror-like sea. Compare that directly to a force 12. A force 12 represents true hurricane force winds, a situation so extreme that the air is literally filled with flying foam and the sea surface turns completely white with driving spray, bringing visibility down to virtually zero. Moving right along to Section 3, rogue waves and surges. But here's the thing, wind is literally only half the battle. When it comes to coastlines, the true horror is the storm surge. Think of this as the heaviest hand of the storm. We aren't just talking about a big wave crashing and retreating. It's a broad, continuous force driven by those immense winds, steadily pushing enormous volumes of seawater toward the coast. It essentially lets the ocean climb right up onto the land, turning coastlines into rushing rivers, tossing cars aside, and cutting off entire communities in minutes. Meanwhile, out in the deep open ocean, sailors used to whisper these terrifying legends of rogue waves. Now, these aren't your typical, predictable storm swells. A rogue wave is a massive, rule-breaking wall of water towering more than twice the height of the surrounding sea. They form dynamically when different wave systems collide at just the perfect angle or when ocean energy concentrates unexpectedly. And the scariest part? They appear with absolutely zero warning, capable of swallowing vessels whole. 25.6 meters. That is exactly 84 feet. For literally centuries, rogue waves were treated purely as myths, just tall tales told by exhausted sailors. But on January 1st, 1995, those legends became a terrifying, undeniable scientific fact. On that New Year's Day, the Droughtner gas platform in the North Sea was taking an absolute beating from a heavy storm. A downward-pointing laser rangefinder rigged to the platform recorded a staggering 84-foot wave striking the steel structure. The surrounding storm waves were only averaging about 39 feet high, making this one singular wave more than twice as tall as its neighbors. It proved the long-whispered legends were absolutely real, and it completely shocked the global scientific community. Which brings us to Section 4, How Ships Survive. So knowing that 84-foot anomalies are out there, lurking in the dark, how on earth do our vessels survive this relentless pounding without shattering into pieces? Well, it's all about brilliant engineering. If a ship is entirely rigid, it is in serious trouble. Take the WWI Liberty ships, for example. Because of their rigid, welded design, the sheer differential force, like a wave listing the bow while the stern drops into a trough, could literally snap the ship right in half. That's exactly why modern ships are engineered with a flexible hull structure. They are built to bend, warp, and dynamically absorb the ocean's immense stress.
But beyond the build of the ship, survival comes down to the crew's tactics. A well-trained crew knows they have to steer the bow directly into the oncoming waves, cutting through the water instead of fighting it. If you take a massive wave broadside, on the long, flat side of the ship, you're highly likely to roll over and capsize. Oh, and most importantly, stay in deep, open water. Stay as far away from unyielding rocks and reefs as possible. A ship can handle a lot of water, but it absolutely cannot handle being relentlessly pounded against a solid object.
It all boils down to what marine engineers call the ping-pong ball analogy. I know, it sounds a bit silly, but an enclosed ship really does function like a ping-pong ball in an angry bathtub. Because it displaces water and is full of buoyant air, it will naturally ride up and down even the steepest, most violent wave troughs. As long as those hatches remain tightly sealed, the bow is pointed into the waves, and the hull stays intact, the ocean's energy spreads out evenly, letting the ship survive just unimaginable heights. Section 5. A warmer, wilder future. So we've engineered our way to survival so far, right? But the ocean's baseline is shifting right beneath us, 21%. According to a landmark study using 15 years of precise NASA satellite data, scientists found a direct measurable link between sea surface temperatures and severe storms. For every single degree Celsius, or 1.8 degrees Fahrenheit, that the ocean surface temperature rises, there is a staggering 21% increase in the formation of extreme storms. And this brings us right back to our very first point about how these monsters are born. Heat equals fuel. Since hurricanes feed directly on the heat and moisture radiating off the ocean, a warmer world acts exactly like pouring high-octane fuel into these engines of chaos. It gives the storm vastly more energy to intensify much faster. We're talking leaping categories in under 24 hours. And it allows the atmosphere to hold way more moisture, which leads to vastly heavier, more destructive rainfall. To put that into perspective, if current carbon trends keep up, climate models project that tropical ocean temperatures could rise by 2.7 degrees Celsius by the end of the century. If that heat gets absorbed into the water, the data suggests we could see the frequency of extreme, devastating storms driven up by an astonishing 60% compared to our current baseline. Now, throw rising sea levels into that turbulent mix, and the threat multiplies exponentially. Tomorrow's heavy storm surges are going to start from a permanently higher baseline. That means the exact same storm hitting the exact same coastline decades from now will push catastrophic flooding significantly deeper into our coastal cities. And it's important to remember, the ocean isn't acting out of malice, it is simply relentlessly physically responding to the heat and pressure we've added to the system. Despite all our incredible engineering brilliance, our flexible hulls, and our high-tech satellites, the raw power of the sea remains completely untamable. Every seasoned sailor knows one universal truth. The ocean is never conquered. It is only endured for one more night. We've absolutely learned to ride the maelstrom, adapting to survive the extreme forces of nature. But as that maelstrom grows ever more violent, fueled by a warming planet, we're left with a truly urgent question. As we continue to pump more heat into this engine of chaos, will our current maritime engineering and coastal planning really be enough to endure the waves that break all the rules? Thank you so much for joining me for this explainer. I hope this fast-paced dive sparked your curiosity, and I will see you on the next one.